Since we've been talking a bit about the different phases of matter and how they behave, we're going to focus in today on gases. The combined gas law is actually a formula on the back of your reference tables. It's in the table in the section labeled combined gas law right here. You can see that the P represents pressure, V is volume, and T is temperature. The 1 as the subscript just means the initial setup, and the P means the final. So something's going to change from one side to the other. And you may have already completed the combined gas law with your lab group. And what you did was you took really, really hot air in a flask and you cooled it down by submerging it in cold water. And as a result, that air needed to be a smaller volume. So as soon as you allowed water to enter the flask, it sucked it in, and you could figure out the volume of the gas that shrunk. So we're going to start working with that formula now. So this is mostly just algebra. And the formula, to write it down, P1 V1 over T1 is equal to P2 V2 over T2. It's actually a combination of a few different formulas all into one. That's why we call it the combined gas laws. STP is actually something we use quite frequently as one of the sets of conditions for the combined gas law, and recall it means standard temperature and pressure. Standard temperature and pressure is actually given on the front of your reference tables in Table A. So those values are right here. Depending on the units you'll be using, you'll either use the standard pressure as 101 kilopascals or 1 atmosphere. And to determine which you're going to use, you're going to look at the numbers you're given. Completely different with temperature. You never use Celsius temperature in the combined gas law. You can't. If you do, you won't get the right answers. You always have to convert to Kelvin. And if you ever forget how to convert to Kelvin, it's actually the last formula in Table T right here. So whatever your Celsius temperature is, you're going to add 273 to convert it to Kelvin. Now we're going to do some math that might be a little difficult, at least traditionally. I've seen that it's difficult for my students. But what I find is students don't write letters wrong when they're rewriting equations. They tend to write numbers wrong though. So what I'd like to do, we're going to attempt to solve that combined gas law for different variables within the gas law without substituting any numbers. If you never do it again, that's fine. I want to show it to you because you may find that the mistakes you make are because you've copied something wrong. Sometimes it's also because you've forgotten what you're solving for and you end up multiplying instead of dividing. So we're gonna go ahead and attempt to solve these for specific variables. So here's our initial equation, like so. I want to solve for P1. So in order to get P1 alone here, I have to get rid of V1 and I have to get rid of T1. So let's start by dealing with T1. Probably what you're going to want to do is cross multiply, and then you're going to want to, divide to get rid of whatever P1 is multiplied by. And we can do that. I'll show you how to do it that way. It's probably not the way that I would do it, but I know they do math a little different now. So if I multiply P1 V1 times the denominator on the other side, that's T2. And then that's going to be set equal to what I cross multiply here, and I'll have P2 V2 times the T1, the denominator on the other side. So I'm still trying to get P1 alone, so in order to get rid of these variables, I need to divide. So I'm going to divide by V1 T2, and now these all cancel out, and you are left with P1 is equal to P2 V2 T1 divided by V1 T2. Now you can just plug your numbers in and solve. So again, we're starting with the same equation. And this time we're going to solve for V1. So probably what you're going to want to do is cross multiply again. I'm going to show you a different way, and it actually eliminates some steps. If I wanted to get V1 alone, getting rid of T1, since it's in the denominator, we would multiply by T1, right? So I'm going to multiply by T1, and I have to do that to this side too. Wouldn't it end up in the numerator when we multiply? So I'm going to just slide that right into the numerator. Now these cancel out. If I wanted to get rid of P1, since it's multiplied, I'd have to divide by P1. So I'm going to do that on this side. And when I do that on the other side, does it not end up in the denominator? There it is. Now these cancel out, and I have V1 is equal to P2 V2 T1 divided by T2 P1. So that's another way to do it. You may still be compelled to do the work of cross-multiplying, and that's fine. I want you to do whatever works for you, but I wanted to show you that method. I'm going to show you one more time in this last one. Oh, maybe not. This one we probably do have to cross-multiply to figure it out. So since T1 is in the denominator, this is often really tricky for students. So we're going to cross-multiply for sure on this one. Let me do my work over here. So we'll have P1 V1 times T2. That's the denominator. So I just did this. Set that equal to P2 V2 times T1. So I just did this. All right. Now to get T1 alone, which is over here, I'm going to need to divide by P2 V2. So now these cancel out, and I have T1 is equal to P1 V1 T2 divided by P2 V2, which is great. But let's see how this works with numbers. All right, here's our first question. A gas has a temperature, so this is going to be the temperature 1 of 120 Kelvin, and a pressure, okay, so this is P1, of 2 atmospheres, at a volume, so this is V1, of 16 liters. What will the new volume, so we are looking for V2, of the gas be at STP? So our P2 is going to be, looking at table A, since our already given pressures in atmospheres, we're going to use the atmospheres value for the pressure. So that's 1 atmosphere. And T2, we always want to use units of Kelvin because Celsius doesn't work for this equation. So our Kelvin temperature at standard temperature is 273. The Kelvin temperature for T1 was already given to us, so we don't need to convert that. Now our equation. This first one I'm going to do by solving first for the variable using just the letters and then substituting in the numbers. So we have P1 V1 over T1 is equal to P2 V2 over T2. We're going to be solving for V2, so I am going to need to divide by P2 and multiply by T2 to get these to cancel out, which means that T2 is now in the numerator on the other side and P2 is in the denominator. So now I can plug my numbers in to solve for V2. So we have T2 first, so that's 273 Kelvin, and then P1, which was 2.0 atmospheres, and then V1, which was 16.0 liters, just getting that from the question. And then in the denominator we have P2, which is 1 atmosphere, and T1, which given in the question was 120.0 Kelvin. Our kelvins are going to cancel out, our atmospheres are going to be canceling out, our units for volume will end up being liters. And now to do some math. So we're going to, in the numerator, multiply 273 times 2 times 16. And I notice in my denominator here, this is a 1. So I don't really need to divide by 1, but I do need to divide by 120. So even though the number I got in the numerator was 8,736, I don't need to necessarily write that down because I'm only going to do one more operation and divide by 120. And I get, 72.8. And remember, our units for volume this time are liters. And the units for volume can really be anything. What really matters is it has to be in Kelvin temperature, and whatever pressure units you were given, you're going to have to give the same units for the standard. So that's how you do that. I'm going to do one more with you, and then the others we're going to do as you pause the video and try it yourself. The next one, a gas at standard temperature and pressure. I'm not going to write down my value for pressure yet because I need to read the rest of my question before I can decide if it's going to be atmospheres or kilopascals. The volume is 359.5 milliliters, so that's V1. They want to know what the new volume will be, that's V2, of the gas, when the temperature changes to 75 degrees Celsius. Okay, we have to convert that to Kelvin. So I'm going to convert that to Kelvin by adding 273, and our T2 will be 348. And then it says here constant pressure. Since the pressure is going to be constant, we can actually eliminate it from the equation. Let me show you what I mean. Normally, it's P1V1 over T1 is equal to P2V2 over T2. Since the pressure values are going to be the same on both sides, we're actually going to eliminate it from our equation altogether. Just like that. They'll cancel each other out. It's going to make it a lot easier for us if we just don't even include it. So now to get V2 alone, which is what we're solving for, we're going to need to multiply by T2 on both sides. So I'm going to multiply by T2. That cancels out, and that's going to put that in the numerator here. So now we can substitute in our numbers. T2, we said, was 348 Kelvin. V1 was given to us as 359.5 milliliters. And T1, we said it was standard temperature, so that's 273 Kelvin. Our kelvins are going to cancel, and our units are going to be in milliliters. So 348 times 359.5 divided by 273. And we get 458, and I'm going to just round this to one more place here, 0.3. That seems like a strange number. I'm going to check my work real quick. 273, and I got it again, so I feel confident that's milliliters. All right, I'm going to have you try the next one, and we're going to actually have you answer it in Edpuzzle. So go ahead and pause the video or wait until you calculate it to enter your answer into Edpuzzle. All right, so here's the answer, and I've worked it out. If you didn't get the correct answer, which we can see over to the right here, you might want to follow through my work to figure out what I've done and maybe identify what you did wrong. The last little part we need to do is talk about some conditions for ideal gases. Ideal gases don't truly exist. They are fictitious. They're the perfect gas, and they don't really exist, but under certain conditions, gases can act very much like ideal gases. And those conditions are really, really high temperature and really, really low pressure. The reason why they act like ideal gases under those conditions are because the molecules are so far apart from each other and moving so quickly that they show very, very little attraction between the particles, and that's what we're looking for in order for it to behave like an ideal gas. The behaviors of an ideal gas are that they move in a straight line path, and by that, think of pool balls on a pool table moving around the table. They move in straight lines if they don't have any spin to them. Okay, those of you that play pool know that you can put a little spin on the ball and make it go curved, but we're talking about only going straight lines, so hitting it straight on. During collisions of those particles, the gases transfer their energy. Is it 2 R's? I think so. Okay. Also, because they are so fast moving and very little pressure going on here, the volume of the gas is negligible. And that just means it's so little that it's not even measurable. And then the most important part is that the molecules are not attracted to each other. And that's probably the hardest thing to do because they do always have attractions to each other. So usually what they'll do is they'll ask this in terms of a multiple choice question, and they'll either center on very high temperature and very low pressure, and then the gas itself needs to be really, really small. So usually if they have a list of choices of gases, you're going to pick the one that's hydrogen or helium at a really high temperature or low pressure. And that's it for these notes.